Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, distinguished guests, participants, ladies and gentlemen. Good afternoon and welcome to the Department of Mathematics, Faculty of Mathematics and Natural Science, Universitas Gadjah Mada, Yogyakarta. Before we explain what the event today is, let me welcome our special invited guests who spared their valuable time to make this event so meaningful for us. Her Excellency, Dr. Norma Yulia Megawati, the Secretary of the Department of Mathematics, Universitas Gadjah Mada. Her Excellency, Professor Indah Imnia Wijayanti, the Chair of Algebra Laboratory, Department of Mathematics, Universitas Gadjah Mada. The distinguished speaker of this colloquium, Dr. Zhang Ruixue, and all participants of this colloquium. First, please allow me to introduce the speaker today. So, Dr. Zhang Ruixue got her PhD at National Institute of Education, Nanyang Technological University, Singapore, under supervision of Dr. Dong Feng Min, and she is working on graph theory. And for today, she will share about her research related to zero-free intervals of chromatic polynomials of mixed hypergraph. Before we start the main agenda, next we kindly invite the Secretary of Department of Mathematics, Universitas Gadjah Mada, to deliver opening remarks and to open the program officially. So to Dr. Norma Yulia Megawati, please.
Thank you, Pak Uha. Your Excellency, Professor Dr. Indah Emilia Wijayanti, as head of the Algebra Laboratory. Your Excellency, our speaker today, Zhang Ruixue. I don't know how to.
Yeah, it's correct. Zhang Ruixue.
Yeah, sorry, Zhang Ruixue, right?
Yeah, correct.
Okay, Zhang Ruixue. And also, for all of the participants of the Algebra Colloquium. Assalamualaikum warahmatullahi wabarakatuh. May peace and God blessing be upon you all. On behalf of the committee, first of all, allow me to extend my warmest greeting and welcome to the Algebra Colloquium, organized by Algebra Laboratory, Department of Mathematics, Universitas Gadjah Mada. One of the goals of this event is to improve the academic atmosphere in the university with the theme of zero-free interval of chromatic polynomials of mixed hypergraph. Is aimed to pull together researchers, educators, and students to share their critical thinking and research outcomes. Distinguished guests, ladies and gentlemen, this colloquium will be far from success, and we could not accomplish what we do without the support from various parties. So let me extend my deepest gratitude and highest appreciation to our speaker, Zhang Ruixue, PhD. And I would also like to thank each of the participants for attending. Should you find any inconveniences and shortcomings, please accept my sincere apologies. To conclude, let me wish you a fruitful discussion. And with that, I declare the Algebra Colloquium open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. I'll give you back to Pak Uha.
Okay. Thank you very much, Bu Norma, had already opened this program officially. Next, may we now ask all invited guests and participants to join for group photos. Please turn your camera and pose for group photos, please. I think one picture should be enough. So we have one slide here. Yeah. So we will give you maybe 1 minute to turn on your camera. Yes. Okay. Wow. Okay. Any other? Okay. So please look at your camera. So not your screen, because if you look at your screen and then you will be like seeing at the bottom. Okay. So I think we can start our group photos. So 1, 2, and 3. Smile. Okay, thank you very much. I think I will send this to Dr. Dong also. Is it okay? Okay. Okay. So thank you very much for everyone for joining the group photos. And next, we arrive at our main agenda, the presentation from Dr. Zhang Ruixue. So please.
Okay.
Okay. Yeah.
Can I share my screen?
Yes. It's already.
Okay.
Yeah. Okay.
Okay. Thanks, Waha, and thanks a lot everyone for coming today. Also, many thanks to the University of Gajah Mada, right, to organizing this colloquium and giving me this opportunity to present my work and share my work with you. Okay, let's start. Today, my topic is about zero-free intervals of chromatic polynomials of mixed hypergraphs. This work, this talk was based on the joint work with my supervisor, Dr. Zhang, and has another PhD student, Bejo. And our paper was published in the beginning of this year in the Journal of Mathematics. Okay. This is my outline. So in this talk, we have 3 parts. In the first part, I like to introduce some basic concept of mixed hypergraphs and their colorings. And in the second part, I will introduce some properties and computations on chromatic polynomials of mixed hypergraphs. And in the last part, I'm going to present my results. Okay, let's begin the first part. So what is the mixed hypergraph? I think most of you know what is a graph or hypergraph. So what is a mixed hypergraph? A mixed hypergraph consists of a vertex set X and the 2 subsets C and D of the power set of X. And the members in C and D are called C edges and D edges respectively. So from this definition, we can write the C edge side and the D edge side like this one. I think from this definition, you may think, so what is the difference of C edge and the D edge? What's the difference between C edge and D edge? Actually, they are different only when we color a mixed hypergraph. Otherwise, actually, they are the same as is a graph. So let's look at how to color a mixed hypergraph. So for any positive integer lambda, a proper lambda coloring of a mixed hypergraph is an assignment of lambda colors to vertices in H, such that each member in C contains at least 2 vertices assigned the same color, and each member in D contains at least 2 vertices assigned different colors. Okay, so clearly we can see that a hypergraph, I mean the traditional hypergraph, is actually a mixed hypergraph without any CH. So when we color a hypergraph, we just satisfy this condition. Each member in E in D contains at least 2 vertices assigned different color is enough. So we see that mixed hypergraphs are generalizations of graphs and hypergraphs. Another interesting thing for mixed hypergraph is that we know that it is possible that the intersection of C and D is not empty. So in that case, each element in C and D is called a B edge. So according to this definition, we can see that in the proper coloring, for a B edge, they have contains at least 2 vertices assigned a common color and at least 2 vertices assigned different color, which implies that for every B edge, the size is greater than or equal to 3. I mean, greater than 2, right? So here is an example for a proper 3 coloring of a mixed hypergraph. Now, usually I draw the solid closed curve represented the D edge, and the dotted closed curve represent the C edge, and dashed closed curve represented the B edge. So in this hypergraph, E1 is a B edge, and E2 is a D edge, E3 is a C edge. You can see that for this one, E1, because it is a B edge, So there are two vertices colored with the same color, and at least the two vertices have the different colors. And E2, because it is a D edge. So for these three vertices, we color them with the three different colors. And because E3 is a C edge, so we can color them by only one color. So this is a proper color of a mixed hypergraph. Okay. The mixed hypergraph, this concept was introduced by the Wallenson in 1993. And he also wrote this book, Coloring Mixed Hypergraphs, Theory, Algorithms, and Applications. And in this book, he introduced the basic theory about mixed hypergraphs, and also posed many open problems about mixed hypergraphs. So if you want to learn more about mixed hypergraph, I recommend you to read this book. Another interesting topic in mixed hypergraph is the calibrable problem. We know that for any hypergraph H, there is a proper K coloring of H whenever K is large enough. So as long as K is greater than the size of the vertex, the vertex site, so we give as long as K is greater than the size of the vertex, then this hypergraph must have a proper coloring. But for a mixed hypergraph, this property does not hold. So you can try in this mixed hypergraph. There are two CH and for 5 DH. If because these two vertices connected by a DH, so these two vertices have be colored different colors, and these two also, and these three vertices also forms a CH. So these two have to be the same color. Then these two also same color, but these two connected by a DH. So we cannot color these two vertices. So for any K, for any positive K, the mixed hypergraph is one, admits no proper K coloring. So for such mixed hypergraph, we call it is the uncolorable. And for a mixed hypergraph, it's called colorable if it has at least one proper K coloring. Okay. So now we are ready to introduce the chromatic polynomials of mixed hypergraphs. We have known that how to color a mixed hypergraph. So chromatic polynomial is a function counting the number of proper colorings of a mixed hypergraph. So from this definition, you can see that chromatic polynomials of mixed hypergraphs are generalizations of chromatic polynomials of graphs and hypergraphs, because all they are counting the number of proper colorings of H. And you know that if H is uncolorable, then its chromatic polynomial must be equal to 0. So forth. Now let's look at an example. This is a mixed hypergraph. We can calculate its chromatic polynomial together. So this is a DH and this is a CH. We can start from this point. Even if you give me lambda colors, for this point, we have lambda ways to color it. And because these two vertices in CH are in CH, so we have to avoid these three vertices colored by three different colors. So we have lambda square minus lambda minus 1 times lambda minus 2 to color these two vertices. And similarly, because these three vertices are in DH, so we have lambda square minus 1 to color these two vertices. Then we got a polynomial. Its chromatic polynomial is this one. And you see that if a mixed hypergraph have more vertices or more edges, we cannot use this method to calculate its chromatic polynomial. So in the next section, I'm going to present some method to calculate its chromatic polynomials and also introduce some properties about the chromatic polynomial of mixed hypergraphs. Now, the first property is a trivial result. It shows that for any mixed hypergraph H, if there exists C0 belongs to C, that means there exists some CH, such that for any pair of vertices XY in C0, they forms an DH. Then its chromatic polynomial is equal to 0. For example, like this picture. This is a CH, and in this CH, every two vertices forms a DH. Then we can now color this edge. So his chromatic polynomial is equal to 0. Actually, in this CH, all vertices forms a complete graph, right? A complete graph, and the two vertices form an edge. Now the second result shows that if there is some edge containing another edge of the same type, then we can removing the large one, and we got a new mixed hypergraph, which has the same chromatic polynomial with the original one. For example, in mixed hypergraph H, C1 is a subset of the C2. And for a proper coloring, if C1, this CH satisfies the proper coloring of condition, then C2 must be satisfied the condition. So C2 is meaningless. We can remove it. That means H and H minus C2, they have the same chromatic polynomial. So this example is for C, and for D, also the same. So based on these properties, we need to give the following two concepts. Now, the first one is reduced. A mixed hypergraph is called reduced if no edge is a subset of any other edge of the same type, and the size of each CH is at least 3. And the reduced subhypergraph, for any mixed hypergraph, we define the reduced subhypergraph H star to be the maximum reduced subhypergraph among all the subhypergraphs of H. So actually, the reduced subhypergraph H star is obtained from H by removing all edges which contain another edge of the same type. So it's clear that H star is uniquely determined by H. And if a mixed hypergraph H is reduced, then H star is equal to H. So based on this concept, we got this property that H is a mixed hypergraph and H star be the reduced subhypergraph of H. Then they have the same chromatic polynomials. Okay, now I'm going to introduce some results on computing chromatic polynomials of mixed hypergraphs. It is well known that deletion contraction formula provides us with a recursive method for computing chromatic polynomials of graphs. That means if we want to calculate a graph's chromatic polynomial, then we can using delete one edge and contract one edge. Here, G minus E is obtained from G by removing E, and G contract E is obtained from G by removing E and identifying all vertices of E as one vertex. And further, Jonas proved that this formula is also applicable to chromatic polynomials of hypergraphs. So actually for mixed hypergraphs, we also have the similar formula. And before we present deletion contraction formula for mixed hypergraph, we need some operations on mixed hypergraphs. Now the first one is identifying. So let H be a master hypergraph, and the X0 is a subset of X. So the master hypergraph H identifying X0 is obtained from H by removing all D edges, with D is a subset of X0, and removing all C edges with the intersection of C and X0 is greater than 1, and identifying all vertices in X0 at one vertex. So we have 3 steps. And you can see that H identifying X0 is actually a master hypergraph, and its vertex side is X minus X0 union a new vertex W. And its CH side and DH side can express as these two formulas. The CH in the hypergraph H, for those C, the intersection with the X0 is empty, then this C is still in this hypergraph. For D also, and if the intersection is greater than is equal to 1, then the CH like this one. Another operation is contracting. For any edge E, let H contracted E denote the master hypergraph H minus E and identifying E, where H minus E is a master hypergraph that will remove E from H. And we see that H contracted E is obtained from H by contracting the edge E. So it is clear that for any calibrable master hypergraph H with a CH C of size 2, if the size is equal to 2, then its chromatic polynomial is equal to H contracted E. So for any CH of size 2, actually is the same with as a vertex. So they have the same chromatic polynomial. So we need only to consider the master hypergraph H satisfying all CHs, the size is greater than 2. So now we are ready to study the deletion and contraction formula for master hypergraph. If H is a calibrable and reduced mixed hypergraph with at least one DH, then for any DH, its chromatic polynomial can be expressed by H minus D and H contracted D. Here we see that our condition is the D is not empty set, and for the case of D is empty set, so we also get the similar formula for computing chromatic polynomials of mixed hypergraphs. But here I will not introduce it because we will not use it. Okay. This theorem shows an alternative expressions for the deletion contraction formula. We can see that if H is a calibrable and reduced mixed hypergraph, so for any two vertices X and Y, with the X and Y is not an DH, then its chromatic polynomial can be expressed H plus D XY and H can identifying XY, where H plus D XY is a master hypergraph obtained from H by adding a new HD. So this theorem and the deletion contraction theorem, actually they are the same. This is the deletion contractions transformation. So applying the above formula repeatedly, we got the following result, which is useful to prove our results. This one. If H is calibrable and reduced mixed hypergraph with at least one CH, and let C0 with its size is greater than 2. So for CH, if there is just at least two vertices which are not from a DH, then its chromatic polynomial can be expressed as this one. So we in C0, there are at least 2 vertices which does not form a DH. Then we can apply this theorem. Then got its chromatic polynomial equals this one. Okay, now above 3 results is about the computing of chromatic polynomials of mixed hypergraphs. Now I'm going to present some known results on the locations of chromatic zeros of graphs and hypergraphs. First is about graphs. In 2004, Soka showed that the zeros of chromatic polynomials of graphs are dense in the whole complex plane. This is for graphs. And for the real zeros, it is well known that these 3 intervals are the only 3 maximum zero-free intervals for chromatic polynomials of graphs. This for all graphs, these 3 intervals are zero-free. But for the certain subset of graphs, Thomason showed that if G is any graph with a Hamiltonian path, then its chromatic polynomial is zero-free in this interval. And Dong and Jackson proved that for any 3 connected planar graph, its chromatic polynomial is zero-free in this interval. So this result is about the locations of chromatic zeros of graphs. And for hypergraphs, in 1995, Domain showed that for any hypergraph in which each edge has even size and each cycle contains an edge of size 2, its chromatic polynomial is zero-free in the intervals -infinity to 0. And recently, we extended Domain's result to a larger family of hypergraphs and proved that the extents of families of hypergraphs whose chromatic polynomial are zero-free in the intervals from -infinity to 0 and from 0 to 1. And also in 2017, we proved that the chromatic polynomial of hypergraphs have dense real zeros in the set of all real numbers. So these are the results about locations of chromatic zeros of hypergraphs. Now it is natural to ask, how are the locations of chromatic zeros of mixed hypergraphs? Now I will present our results about the locations of chromatic zeros of mixed hypergraphs. First, I need to define the cycle in a mixed hypergraph, which is a little bit different from cycles in graphs and hypergraphs. We can see that H is a mixed hypergraph, and a cycle in H is defined to be a sequence of alternating vertices and edges. That's this one. And all this work, V1 and Vt are distinct vertices. And EI is not equal to EJ whenever EI and EJ are not BH. That means EI and EJ is not in C and D. Such that Vn and Vi plus 1 is the subset of EI. So we can see this graph, H1. In H1, this is a cycle, and this is a cycle. This is also a cycle. And according to this definition, we can see H2 because E is a BH. So actually this one we also regard it as a cycle. So in mixed hypergraph, this one we also regard it as a cycle. Okay, based on this definition, another one. For a cycle, if all these edges are D edges, then we call this cycle is a D cycle. So based on these two definitions, we can define a family of mixed hypergraphs in Q0. let Q0 be the set of reduced mixed hypergraphs satisfying the following conditions. Now, the first condition is for each DH, its size is even. And the second condition is for every D cycle, there is an edge. There is a DH of size 2, which is the union of DI. So for every D cycle, there is a DH of size 2, which is the union of DI. And the condition 3 is for every cycle, which is not a D cycle. So there is an edge V1 and VG. That means a DH of size 2. And V1 and VG is the subset of Vi until Vt. So this Q0 is a family of mixed hypergraphs. We can look at this example. H1 is not in Q1, and sorry, H1 is not in Q0 because this 2CH forms a cycle which is not a D cycle, but there is no DH of size 2. But H2 is a D cycle, is in Q0, it's in Q0. And we can calculate their chromatic polynomials. For H1, its chromatic polynomial equal to this one, and we calculate its zeros. There is a real zeros at -2 minus 2 square root 2. And for H2, its chromatic polynomial is this one, which shows that there has no real zeros in the intervals from -infinity to 0. So we got our main result, the first main result. For any calibrable mixed hypergraph H in Q0, its chromatic polynomial has no real roots in the intervals from -infinity to 0. And this result actually extends the known results regarding zero-free intervals of chromatic polynomials of graphs and hypergraphs. The second result is based on another family of mixed hypergraphs, the Q0 prime. Q0 prime is actually a subset of Q0 and satisfies that the spanning subhypergraph XD2 is connected, where D2 is all edges of set 2, all DHs of set 2, all DHs of set 2. For example, H1 is not in Q0 prime because this spanning subhypergraph is disconnected, while H2 is in Q0 prime because this spanning subhypergraph is connected. Then we prove that for any calibrable mixed hypergraph in Q0 prime, its chromatic polynomial has no real roots in the intervals from 0 to 1. So based on these two results, we can see that for any calibrable mixed hypergraph in Q0 prime, its chromatic polynomial has no real roots in these two intervals. Okay, now I'm going to introduce our main idea of our proofs. Actually, we prove these two results, these two theorems by induction on the number of C edges using deletion contraction formula and their transformations. So we have to show that Q0 is deletion and contraction closable. So that means that for any mixed hypergraph H in Q0 with at least one edge, this edge can be C or D. And at least one of the following cases happens. Now the first one, there is just some D zeros, there is some D edge such that H minus D and H contracted D are in Q0. The second one is there is just some C edge such that H minus C and H contracted X0, where X is a subset of C, are in Q0. In our last paper is about zero free intervals of chromatic polynomial of hypergraphs. We have proved that for any reduced mixed hypergraph H in Q0 without any CH, then H minus D and H contracted D are in Q0. So in this paper, we discuss the case of mixed hypergraphs in Q0 with at least one CH. So if we want to show that H minus C and H identifying X0 are also in Q0, we have to show that these two mixed hypergraph satisfies these three conditions. So the hard part is to prove that they satisfy the condition 2 and the condition 3. Let's go back. We want to show that these two mixed hypergraphs also satisfy the condition 2 and condition 3. So we studied the hypergraphs which satisfying condition 3, the structure. We studied the hypergraph that the structure of mixed hypergraph satisfying condition 3. Now we got the first result. H is a reduced mixed hypergraph satisfying condition 3. Then for any distinct pair C1 and C2 with their intersection is greater than 1, then for any pair of vertices in C1 and C2, they forms a DH. And also for any CH and DH, the intersection is less than or equal to 1. And if H is calibrable, then the intersection of C and D is empty. And this result shows the structure of mixed hypergraphs satisfying condition 2. And this two result is study the mixed hypergraphs satisfying condition 2. For this one, for any D0 with the size is equal to 2, then we contract D0. We got the DH is the subset of this one. So based on these three results, we got our result that for any mixed hypergraph with at least one CH, then H minus C and H can identify X0 are also in Q0. So based on these 4 results, we can prove our theorems. Okay, thank you.
Wow, thank you very much. That's a really nice presentation. So please give big applause or press the clap button in the reaction to Dr. Zhang. Okay, so next we will start with the Q&A session. Maybe any question or anyone maybe want to turn on the microphone about hypergraph, because yeah, I'm not that sure, but I think for almost all of us it is new enough for us, because some of us are working on the graph theory, not focus on the hypergraph part. Or maybe any comments?
I think because not many people knows mixed hypergraphs, right? It's quite new. Although it was proposed.
Okay, yeah, Professor Indah maybe.
Just I want to know in which part you mean the mix here?
Sorry?
What is the different hypergraph and mixed hypergraph?
The difference.
The difference, yeah. Hypergraph.
When we coloring, because for hypergraph, actually they only have DH. For hypergraphs, they only have DH. When we coloring it, for just satisfy, we can see, they just satisfy this condition. So for a hypergraph, but for mixed hypergraph, they have C edges and D edges. So they have to satisfy these two conditions. Yeah. So hypergraph is actually a mixed hypergraph without any C edge.
Oh, okay. When C is empty, then you have a hypergraph.
Yeah.
Okay.
So this one is the special condition of hypergraph. Okay, maybe next, Mr. Adrian. Okay.
Hello, Ruixue.
Hi.
Okay. This is new for me. I remember when you start your PhD, even before you start your PhD, you already do some hypergraph, right? And in the beginning of your PhD, I remember. Okay, we read the chromatic polynomials definition together at the time, and then you try to find the difference. You compare the chromatic polynomials for graph and hypergraph, right? I remember you got one paper on that, and also at the end of your PhD, I remember you have a paper. I'm not sure when it is finished, but you had a paper in zero-free interval.
For hypergraphs.
For hypergraph, right? That's why when I saw the title, you are now working in mixed hypergraphs, which I don't know the definition. I barely knew that. Yeah, I barely knew. Okay, and then I'm just curious because you don't you know that I'm not working in graph, right? Although I read some graph theory paper, but I'm not working on that. How long does it take for you to construct this thought moving from hypergraph to mixed hypergraph? Okay, first of all, is it you who define the mixed hypergraph, or is it by someone else? The definition of mixed hypergraph.
Wallenson.
Okay,
this
Wallenson,
guy.
okay. So
this guy.
Yeah. Okay, but not many people try to relate, right? To relate the chromatic polynomials and the hypergraph, let alone the mixed hypergraph. And you got this opportunity, right? And then you see that, and then you work on that, and then you get this zero-free interval, but with mixed hypergraph rather than the normal hypergraph you had before. And how long it takes? I want to know how long it takes from your previous. I think it's very previous paper, right? Your 2020 maybe, because 2000.
Actually, we have got the first. Now you know the paper of chromatic zero-free for hypergraphs. Actually, the first we got the meta hypergraph because hypergraph is the subset of meta hypergraph, and at that time we submit our paper about mixed hypergraph, and they rejected. After that, we delete our paper 2 papers. So the first one is hypergraph is quite easy to publish, and then we change our another one to publish this paper lah.
So actually, the mixed hypergraph came before the hypergraph one.
Yeah. Because hypergraph is just one case of mixed hypergraph. Yeah. Okay.
Thanks.
Yeah.
That's interesting. Oh yeah, thank you very much. Okay, so I get a direct chat here. So I think it is not compulsory to ask in English. So if you want to ask in Indonesian language, I can help you to translate. So if any of you want to ask in Bahasa Indonesia, do I have to say the name?
There's one question from Saifullah Ali.
Okay, yeah. So this one. So it is possible to make a hypergraph using ring theory or group theory or something like in algebraic graph. Is it possible to connect?
I think, yeah. I think because hypergraph is actually the set system, right? The set system. It's like the group theory. I think maybe we can, but I never try.
You see, maybe can we define any, maybe for the edges, maybe from graph theory or from ring theory, maybe the vertex comes from the elements. Is there any research on that kind of stuff? Maybe.
I don't.
It's okay. So yeah, we just curious. Yeah, I think is that answer, Saiful? Is that answer your question? Oh, okay. Thank you. So maybe any more question? We still have around 10 minutes.
For Mixed Hypergraph, there are more problems that need to solve. Like in this book, in this book, they post a lot of open problems, and like what we said, one very interesting topic is about the calibrable mixed hypergraph. What kind of mixed hypergraph is calibrable, and what is the maximum and the minimum of state edges or d edges for a calibrable mixed hypergraph or uncalibrable mixed hypergraph? It's a hot topic, I think. Yeah.
Okay. Yeah, there are some problem there. Okay, so is it okay to answer another one from Musa? Do you want to turn on your mic or just
is there
from the chat
any
box?
relationship?
Okay, so is there any relation? Yeah, hypergraph and hypergroup.
Hypergroup. Oh, sorry, I don't know what is a hypergroup.
Maybe Musa, can you
I'm sorry.
explain more hypergroup theory?
It's like a group theory, right? But I never do any research on group theory. So
actually, there is a explanation also in Wikipedia. But I think need some time also to understand.
Like a group that with numeric operation. I heard that that's something like group. Yeah, I think they have. I think for graph and group, maybe they have some connections.
Maybe there is a way to connect, because when I read the definition, actually this one is more abstract, and maybe what we have to do is defining the adjacency first, maybe. But yeah, still don't know. Okay, maybe any more? If not, maybe from me, I'm curious. Because when I look at the list of participants, there are some of us who are interested in this kind of topic. But yeah, as we mentioned before, like Hadrian mentioned before, that we are new in this kind of stuff. So maybe we are a newcomer. Do you have any suggestion, maybe, or maybe simple problem for the initial point, if we are interested in research related to hypergraph or mixed hypergraph? For the initial point, maybe.
Already you have a paper problem in chromatic polynomials, right? You have a paper. Paper by Zhang Ruixue. Problem. Related to chromatic
you can solve the problems.
You have the paper.
You notice?
Yeah.
Okay.
You read that paper.
And I don't really read it. Not. But actually, I'm curious how you come with the Q0 and Q0 prime. Yeah, that's a question. How you come with that Q0, the class, the class of mixed hypergraph? Q0 and Q0 and the Q0 prime, because that's the point of your result, right? The Q0, the class of Q0 and the Q0 prime. I don't know. I don't know the motivation. Actually, sometimes when someone have a paper, have a result, right, I'm wondering how they come with the definition of that, because let me make it clear. The Q0 is by you or by other.
By us. Actually, we just give its name. Actually, at first we just just we got some a family of meta hypergraphs which satisfies these three conditions, and for easy to write, so we give its name.
You give it the name, and your result is into 0, right?
Yeah. And these three conditions actually from the motivation is from the domain theory, domain results. You see, in his result is for hypergraph for each edge is even size and each cycle contains this one. So we want to extend his result, and we try what kind of meta hypergraph or hypergraph also have such properties. So we extend.
Okay, I see. Now I can see from this the first point, right? That explains a lot. Okay, for that. Okay.
Yeah. Okay, I can catch some problem here. For the starting point. Okay, maybe any more?
Another question.
Okay.
Okay. We took topology together, and I don't know. Maybe you already know that there's a connection between topology and graph, right? Because graph can be considered as topology and also another way around, right? And maybe a silly question also, similar to that of Ali, right? Hyperspace. You know hyperspace?
Hyperspace.
Hyperspace. So you make a topology on the topology. So you have a set, you have a topology, right? And then on the topology, you can make a topology, right? Do you think there's a connection between the hypergraph and the hyperspace? Because graph and topology have a close relationship, yeah. But you don't consider that. Yeah, you don't consider.
Because I know about a little topology. You are topology expert. You should consider this problem.
Yeah, but you are hypergraph expert, so I ask you. Okay, that's okay. Thanks. I think I asked a lot, and now I start to be quiet.
Okay.
Well, I know.
Okay. I think we still have some time. Yeah. Okay.
Yeah. Thank you for the presentation, Dr. Zhang. I just want to highlight the difference between graphs and hypergraphs. In graphs, the edge only connected to vertices, but in this hypergraph, one edge connected
any number over.
So can you tell us what are the simple example just a simple example in daily life, for example, if X is the simple example of hypergraph. So the connection.
This you mean this actually this one you also can.
This one, yeah. Oh, okay. Yeah. So the circle. Circle is this edge, you mean?
Edge. Yeah, but if we don't color it, actually this is a hypergraph. But we color it, this is a D edge, this is a C edge. So for hypergraph, you can see from this definition, for hypergraph, they consist of a vertex side and an edge side E, and the edge side is the subside of X. Yeah. So for hypergraph, each edge can contain any number of vertices, and also can maybe some edge is a subset of another edge. It's okay.
Yeah. So as a counterpart in the structure, for example, the Musa asked about group. Yeah, we know that in group we have a binary operation. Maybe if we have hypergroup, we have n-ary operation. Maybe there is a connection.
Yeah, maybe
somehow.
Yeah, so we can try to use some connection.
Okay, thank you.
Thanks.
Okay.
Thank you.
Is that all? Okay. Thank you very much, Professor Indah. Maybe 1 minute, one last question. Yeah, I'm still thinking about the maybe bus stop and also bus road. Can we see it as a hypergraph, because sometimes one bus stop can be joined with more than one bus, right? Still thinking in daily in our daily life. Okay, no more question. Okay, so since there is no more question, I think we can end our Q&A session. And once more, please give her a big applause, or maybe clap button. That's also fine. One clap button, two clap button, and more. Okay, so before our close our event today, maybe can I share my screen?
Okay.
Okay. Yeah. Okay. Thank you. So we already prepare an e-certificate for you. Yeah. So again, thank you very much for sharing with us today. And yeah, that's really a fruitful discussion also. And maybe before we end our event, is there any announcement, maybe Professor Indah, or maybe another one?
Oh, I think there's a good continuity activity. Every month we can organize Algebra Colloquium, and today we have the special guest from China. Thank you very much, Dr. Zhang. Please come again to Jakarta, maybe face to face with us here.
Yeah.
Stay online, but you come here. It will come. We welcome you to come here. And for all the participants, thank you very much. Terima kasih. Ini akan kita laksanakan secara rutin. Silakan bergabung terus dengan colloquium yang akan datang. Ya, terima kasih semuanya. Thank you very much for all.
Okay, yeah, thank you. Yeah, thank you very much. I think that's all for today, and yeah, it's a good time to end our event. So again, thank you very much for everyone, especially for our friend here, Dr. Zhang Ruixue, for sharing with us. And yeah, I think see you again maybe next month in the same agenda also.
Yeah,
so
I
think that's all. Yeah, good afternoon and wassalamualaikum warahmatullahi wabarakatuh.